Okay, so if you are quarantined or absent, we are going to do a simulation of what we did today in class, which is candy isotopes. So, long story short, we took two types of candy, Smarties and Skittles, and used them to model the ratio of protons to neutrons in different isotopes of an atom. So, before we begin, we're going to go through and do a recap of a couple things. So for step one, the mass number of an atom is the total number of what? So here, it's P for protons plus the neutrons. So P plus N is what we need to do or to add up in order to get the atomic mass. So if you have isotopes of one element, that means you have the same element except the two different atoms have different masses. To have a different mass, you have to have a different number of neutrons. So that's what this simulation is going to specialize in today. If you were lost in what I just said, it's totally okay. That's what we're doing with our simulation. So the next step is carbon 13 is our example problem. So carbon 13 is an isotope of carbon with a mass number of 13. So how many neutrons are in carbon 13? So the first thing that we do is we plug carbon in on the periodic table. When we look up carbon on the periodic table, we're going to see it in the second row. It's going to be a giant C, and there's going to be a 6 in the top of the box. So that means that that is element number 6, and it has 6 protons. To find out the number of neutrons, we take 13 minus 6, and that will give us 7. So there are 7 neutrons. N0 is just, again, the symbol for neutron. So the next step is how many protons and neutrons and what isotope is this picture that we see to the left. So first we count the number of protons. Those are the circles with positive symbols in them. There are 5, so we say 5 protons. Then we go, what is the atomic number? The atomic number is the number of protons, so that will also be 5. What element is this? We find element number 5 on the periodic table, which is going to be right next door to carbon. And that will have a large B for the chemical symbol, and there will be a 5 above it. And that element is boron. So we write boron. And then how many neutrons is this? So the neutrons are the white circles, so we got 1, 2, 3, 4, so that's going to be 4 neutrons. And what is the mass number? So the mass number is P plus N, so that's 5 plus 4 is going to equal 9. And then your isotope name is the combination of the element name and the mass number of that atom. So it's going to be boron 9. Okay, now we get to the part where we used candy to simulate this. We used candy to simulate what we're drawing, so what I'm going to do is give an example of what the candy would be, and then we'll draw it. Okay, so for helium-3, we would first need to find out what number helium is. So we find He on the periodic table, and that will be in the second row, that will be in the first row to the very far right. And that is element number 2. Oh, yeah. Okay, so if helium is number 2, that means it has 2 protons. In this simulation, we use Skittles to represent the protons. So I had people get out 2 Skittles and place them in the box. And then to simulate the number of neutrons, we used Smarties. Well, how many Smarties do we need? So to figure out the number of Smartie neutrons we need, we're going to take the mass number and subtract the 2 protons from the mass number to get the difference, which is the number of neutrons. 3 minus 2 is going to equal 1. So that's going to give us 1 Smartie neutron, and that will be an empty circle. Now we use the candy to model how the atom will be built and how it will be similar yet different between the left box and the right box. So again, every Smartie represented a neutron, every Skittle represented a proton. So at this time I'm going to draw 2 protons where I see a Skittle. And then where I see the Smartie, I'm going to draw my lone neutron. So that is what the atomic nucleus would actually look like, okay? Right there in that box. So that's helium-3. What's helium-4 look like? So helium with a mass of 4, again, helium is our second element. So that's going to mean that we're going to need 2 Skittles. which means that we'll need 2 protons. So the first part of this pattern that we're going to see as we go through this is that your number of protons should be the same between the left box and the right box. What will change is not the number of protons, but rather the number of neutrons that go with them. So in this next example, we have helium with a mass of 4. 4 minus 2 protons gives us how many neutrons? The answer is 2. So helium-4 will have 2 neutrons, while helium-3 will have 1 neutron. Again, they both have the same number of protons. It's just that they need different numbers of neutrons, which is what this was all about up here. So now we know what we're doing. So basically, we just draw the models, okay? And I'll do lithium in a bit. But you'll notice that if you're looking on the campus page, I have an advanced lab and a general lab. The drawing part is the same, but what becomes different is something called percent abundance, which is a weighted average, and then a normal average. So if you're doing the advanced lab, I'm going to explain why we're doing the percent abundance and how to do it. First of all, what's the reason? Well, if you look at the periodic table, you'll notice that the number at the bottom is the mass number, and it's the average mass of all the isotopes of that element. So for example, if carbon says it's going to be 12.011, that means that we have some carbon 12, some carbon 11, some carbon 13, some carbon 14s. And with all those different types of carbon isotopes, how do we get a weird average like 12.011? Why wouldn't it be, say, like 12.5 or 13, like a normal average is? Well, it's because that you have, so many carbon 12s, and then let's do a little bar graph. So here's 12, then you got some 13s, and then you got some 14s, and then you got some 11s. So the thing is that when you look at your carbon values on a chart, 12 is by far the most prevalent form of carbon. And so not all the other isotopes are represented equally. The example I gave in class was this. If we had 3 categories that hair color fell into, which would be red, blonde, and brownish black, would they all be represented equally in the same class? And the answer every period was no, because, so many people have blonde hair, and then maybe more of them had brown hair or less, and then maybe less of them have red hair. So you had different abundances of those hair colors. The same is true for isotopes. Well, if 12 is your most common isotope, the average is going to be closest to 12. So what we're doing here is simulating how to calculate a weighted average where one isotope is represented more so than the others. So what we do is this. To calculate the weighted average, if you're doing the advanced version, is this. You take the 3 from the helium mass number, and you're going to multiply it by the decimal of the percent abundance for helium-3. That means that you first need to take the decimal and move it 2 spots to the left, which will give you a decimal of 0.438. So we take 3 times 0.438 and we multiply it to get a product. And that product is going to be 1.314. So that tells us that 43.8% of 3 is 1.314. Now that we do the same thing for the next side, except we have different numbers. So we take the 4 in helium-4 and we multiply that by the decimal percent abundance of 56.2%, which gives us, again, move the decimal 2 spots to the left first, 56.562. So we have 4 times 0.562, which will equal 2.248. So we add them together. We add these two numbers together, 2.248 plus 1.314, and get our total average. So we get 3.562. And that is your weighted average. So your average atomic mass is the sum of these two products that we got. And that's 3.562. Now why is this important? Well, it's not 3.5, it's 3.56, which shows us that the average is slightly closer to 4 because helium-4 makes up 56% of all helium atoms in this simulation, whereas the remaining 43.8% of the helium atoms are all helium with a mass of 3. So if you have the majority of them being the mass of 4, your average, when it's weighted, should be closer to 4 than it is to 3. So that's how you do a weighted average. Long story short, your first step, take your percents, turn them into decimals. The next step is you take the 4 from the mass or the 3 from the mass or whatever the mass number is, and you multiply it by that decimal for each side, and you get your product. The final step is you add the two products to get your average. You don't need to divide by anything. You don't need to do that. Okay? It's already factored in with the weight. All right, now if you're not doing